Vous m'entendez? Oui. So good morning, good afternoon, everyone. So it's a pleasure to be here in front of you in order to propose you a digital innovation and industrial performance in decommissioning presentation. So I will start this presentation to underline the fact that at CEA we have to manage legacy facilities, and these facilities are mainly R&D facility. And it's important to manage the end life of our facility and waste associated in order to contribute to the development sustainable of the energy, nuclear energy. Yes, so with my colleague Karim Bouguergui, so head of the ionizing radiation instrumentation and metrology services, and myself, Magali Saliden, R&D program manager in support of dismantling and decommissioning operations. So we propose you this presentation. So this presentation is based on 4 different parts. After an overview of the description of the challenges in nuclear dismantling operation and the description of the operational complexity of our operations that we have to manage, Karim will present you different examples and different developments and the place and the role of these tools in our operation. And we conclude by a global approach. So what is hidden behind the dismantling term? So according to the EAA source, nuclear decommissioning covers all steps leading to the release of a nuclear facility from regulatory control. So in this context, dismantling and the waste retrieval conditioning operation are defined by radiological, technical, and organizational complexity. And for example, we have to manage radiological protection and access limitation, technically demanding and confined with high activity environments. We have to manage heterogeneous waste stream, and because our operation take sometimes very long time, we have to take into account the temporality of these different operations. So what are the main operational challenges to arise when dealing with such radiological and organizational complexity? So to answer, I propose you a very slide description, but in order to understand the complexity of our operations that we have to manage, so first of all, we have to take into account a multidimensional system. So efficient dismantling requires balancing between safety, schedule, and technical feasibility through a holistic and system-wide approach. So it's very important to know all the different steps before to start operation. These operations are interlinked from the characterization program to the transportation of our waste in the final disposal, flow, routine, retrieval, conditioning, or packaging operation in order to be able to manage this type of waste. So each step depends on the successful completion and validation of the previous one with a systemic approach. The third axis is the notion of time, safety, schedule, cost grouping. It's essential triptych in nuclear decommissioning approach, and minor deviation can cascade across the entire project timelines. And the last one point concern a lot of time, a high variability of and the uncertainty of our data. And to illustrate it, sometimes we have to manage incomplete waste data and or evolving site conditions which demand adaptability and expert judgment. So in the more precise context, so how can the advanced digital tools help simulate, optimize, and secure such complex operation? So next one, please. So the role of this technology is essential in order to manage all the different steps in our operation. And the beginning of all the operation concerns the characterization, concerns the definition of the initial steps. It's important to have a best of knowledge of the radiological activity of the site, of the facility before to imagine any scenario. The second step concerns the design of the intervention scenario. So in order to define, to develop a study in ALARA approach and to start to simulate to simulate the different operation and equipment. The second concerns a very important part in order to decrease the impact of the radioactivity in contact of our operator. So this step concerns the operator training in immersive training, or in order to be sure that the operation can be managed and in order to decrease the radioactivity in contact of our operator. And it is at the end of these three first steps that we can start the on-file work. And it is only at this step that we can imagine to implemented the system, implemented the tool. And at the end, in order to finalize the cycle, so we have a characterization step to finish in order to define the final state of the facility of the site. So advanced technology, digital technology shifts operation from reactive operational activity to predictive and integrated approaches.
Now, to illustrate this different step, I start to present you several examples of this different approach. For the characterization, especially concerning the definition of initial state, the problem, we need to have the point zero. The point zero is to have a status of the installation. To have this status of installation, we need to have historical data from people, from document, or from different other aspects. And then we need to have a model. The first step is a model. It's not a twin, it's a model. To have this model, we have different solutions. One of the solutions that we developed is concerning not with a GPS, is to do a 3D scan. The 3D scan, you can do that with, for example, these tools, which is 4 different visible camera, is not a specific camera, is only visible camera with 1 EMU. Additional GPS if you have GPS, but if you haven't got a GPS, for example, in indoor situation, you can use this type of tools. You have also a computer because you need to have a whole data information collected to this computer in order to have different aspects of this 3D model. In this example, the first a picture concerning the data acquisition in real time. This means that you have different spots, and this spot is completely connected, for example, with different tools that you can have directly on site. You can, for example, have some detectors, some radiological detectors, and you have a specific position of this, which is connected to these tools directly. After that, you can have, for example, the surface creation, because you have a cloud, a point cloud, and then you can have, if you have time, you can also have a process to calculate the different point, and in this case, you have a surface creation with the textures in order to have a complete 3D reconstruction. This means you can also add some specification like the densification in order to have each point by each point to obtain in the final video like this. This means that you, at the first step, you have the initial, for example, process in order to have a 3D model in which you can have, for example, virtual reality, or you can have for the training the people in order to dimension correctly the different stage of the dismantling. After that, for the design of this intervention scenario. This means that you need to have different calculation. This means, for example, in this case, it's an application. For example, every people know MCNP. MCNP is very useful in order to have the complete model of your system, for example. If you have this model, the main problem is you can have a model of your system, you obtain after that your system, and you test it directly on site. But the difference of the measurement that you obtain on site is really different of your model. And in this case, the only solution is to change some parameters manually and recalculate. This takes a long time. That's why, in this case, we have a tools, specific tools, which is automatically adjust your model for the data that you have directly on site with your systems. And in this case, you have a real copy of you in the digital twin, for example, you have a copy of your systems. The second tool is expressive. What is it expressive? One of the problems today is to have a capitalization of the knowledge of an expert. It's very complicated to have a digital memory of an expert. In this case, you can define some different role with this expert, with some interview, to know exactly his knowledge like a role, digital role, that you put in these systems. And in this case, you can also add to the inference engine, you can also add the data from the sensor that you have directly on site. You have the data from a sensor, you have a knowledge from an expert, and then you can have a decision. But this decision is not like a network. This decision, it's a decision we can explain in real time what is this decision. For example, you just have the information to say, we have this decision because an expert gave me the information that we have this data with this data, and the tools indicate me this data. And in this case, it's not a black box. You can explain exactly what is the decision. But this decision, it's an expert that he can make this type of decision. Another tool is concerning the different sensor that you can have on site. Why? It's an example in this case. What is very important is to have the term system control. What is it, a system control? It's the whole platform that we can collect the data from the sensor and to transfer it directly to your model that we can see with the cloud of point, for example. And in this case, which named SLAM, you can have a whole geolocalization of your measurement. Not the geolocalization of a person to take the measurement, but geolocalization of a sensor. The sensor which is indicate, for example, the distance in which you can make the measurement. And you have this with OmniTracker. You can have alpha, beta, gamma, and neutron measurement. And spec is concerning the whole profile of dosimetry. Newcomoslam, it's a system in which you can, with the same system, have the complete model in 3D model and the data of measurement, which is tagged directly to the point. And then the last one, NanoPix. And these other different tools can connect it directly to this robot, Optimus name, that you can see on the booth of the CEA. For the training aspect is very complicated because you need to have in the past a book, and you say to an expert, read the book and you become an expert. But in this case, it's not possible. That's why we have an approach in which we can collect different knowledge from data, and action. And in this case, we can have a complete virtual or digital twin in which we can training the different people directly on site with reality, virtual reality, or different other tools. And in this case, we can have a complete interactive multi-physics simulation because it's not only radiological aspect, but you can have mechanical aspect, you can have robot, arm. In this case, you have a complete human in the loop because you have a real situation and you have a training for the different people directly with the same data. And in this case, when the person goes directly on site, is familiar with the scenario. Is not something where it's see for the first time, for example. This is an example of what is it for the trainings of two robots, which is used directly on site. This means that we can have, in this case, a virtual reality in which the person can directly train on real time. And in this case, which is this type of tools, it's connected directly to the robot, and we have the answer of the robot. If it's a mistake, if it have a mistake, he have the information. On-field works. I just focus on this, for example, on robotic systems, because robotic system you can see on this WNE edition, you can see everything on robots. It's a real topic because you can have a cobot, exoskeleton, polyvalent gripper arm. But one thing which is very important is, have we got any robot to give information in order to have this virtual reality and augmented reality directly on site? Is it possible to have it? And in this case, we have different tools that we can connect directly to the system to have this type of information. Yep. The characterization, the last step. We see the first step, which is historical aspect of the installation. Collect the data, make the training, have a model, complete model. And we have the possibility also to modify the model. And the last step is interoperability with existing different vehicles. These different vehicles could be, for example, robot, drones, human person, system which is put directly on site, everything. And in this case, you can have a whole measurement which is coming to this type of system. And in this case, you can directly have the whole information. And this, it's a real information that we can need. For example, to have the visual data presentation via an interface or compliance with the field requirements.
So to conclude, now I am sure that at the end of this presentation you are convinced of the necessity to use digital tools in our dismantling and decommissioning operation. So we will underline the fact that decommissioning success depends on the managing of a dynamic system. It's very important to have an iterative approach to perform our operation. where every technical safety and schedule decision is interconnected. So digital integration and safety merging, operational flow and schedule reliability with a safety approach for the different in-zone intervention to enhance the performance of our operation with optimized planning and reduce the downtime. The reliability of our scenario, which can be validated and to reduce the human error, and the traceability of the data with unified and data-driven workflow. So digital integration is a cornerstone of a model, but not only for risk-informed decommissioning strategy. And so to finish, we are happy to answer to your question if you have someone, of course.
Thank you for your attention.